See, you can see this particular that structure B, where we can see there's more uniformity is there, less porosity is there as compared to all others. And relative to others, I'm just indicating, showing you the results because I could finish within 2-3 minutes. So this is I can simply say that 1% addition of this Fe3O4, more uniform structures are there, and because of that we will obtain a good results from this when we are getting 1% instead of that 3 or 5%. Again, this is for other type of alloy. This is the cross section of the coatings. When we obtain the coating, you can just see around 10 micrometer uniform coatings are there. This is also one of the advantages of this type of a system. You will have a uniform coating instead. Otherwise, when we are spraying, then ultimately this is one of the major challenges if you want to coat it uniformly. Again, for other type of alloy, then we make an addition test for all type of coatings, and again, here you can see when we have a 1% that Fe3O4, you will have more uniform. We can say that the coatings are more adhesive at that particular ratio of this magnetite. Both the cases are there. Then again for 2050, you can see for both that 1%, it is around 58% angle is there for 2050. Although all type of samples are provided about 2050, but comparatively it's better for that we have 1% Fe2O3. Again, other type of material. Surface roughness, we can see again there is an increase in the surface roughness as we add the percentage of this magnetite in both the cases. Then if we just go through a corrosion studies, then automatically this 1%, if we say Engg is, I can say less in this case, and even 1% Fe3O4 mixture indicate the maximum corrosion resistance. The corrosion rate is less in that case, in both the cases, not only one but in another case also. Similarly, in vitro biocompatibility is higher when we use this 1% Fe3O4. In vitro biocompatibility, just see the structures which is more uniform, we can say that related to these components, just in fishing. So we just discuss with some of the conclusions, like although we have already discussed, first one is this particular method is successful to coat this mixture of coating on the two types of the alloys, which because we have coated and we have studied in detail or many of the other parameters also, but here I'll just show you a few of the results. Even the results are better when we have a 1% addition of that magnetite. This is because of all the coatings are chemistry, because we have just given a structure for everyone. All type of coating, we have discussed this in also. The depression of Fe3O4 particle in the matrix provides more surface area that allow K2C to penetrate between the bioceramics, both type of HA and BG, and that magnetite particles, which results in improved attachment between the coating layer and the substrate. That's why even when we perform the adhesive test, the addition is higher in case when we have add a 1% of magnetite. Automatically, the composite coating are better porosity. We have all seen these results. Even surface roughness goes on increasing as we increase the percentage of that magnetite. So this is all about the basic results. The contact angles, just you can see the order of corrosion resistance. Higher corrosion resistance is indicated when we have a hydroxy hepatite and silicate bioactive glass and 1% addition of magnetite. That is one of better results. There are more corrosion resistances there in that case as compared to when we have a higher percentage of that magnetite. So these are all the conclusions. There are some, I recommended some suggestions for future work. I think we will discuss it. So this is all about, I think. If you have any questions. Okay, then thank you. I think they have decided that for any type of a question you can send me an email because of time constraints. So thank you again for all of you also for your patience.
Thank you so much, sir. As we are falling short of the time, so if you have any query or questions, you can share it through the email. Now we have with us, I would like to invite Professor Dr. and Chief Professor, Dean Engineering and Technology, to honor Professor Buddha Singh sir. Sir, I would like to invite Dr. Deputy Professor to kindly felicitate and welcome Dr. Palani Kumar, SRM Institute of Technology, Chennai. Now I would like to invite Dr. R. Shankar, Head of the Mechanical Department, to kindly facilitate Professor R.C. Singh from Delhi Technological University, Delhi. Now I would like to invite Dr. Engg Sharma sir to kindly felicitate Professor Rajiv Chaudhary from Delhi Technological University, Delhi. Thank you, sir. Now I would like to request Dr. Palani Kumar from SRM Institute of Technology, Chennai, to kindly deliver his preliminary talk. Thank you.
So 15 minutes only. 15 minutes only. And this talk will start at 5 minutes. थोड़ा चार्जर निकला था ना लैपटॉप का, तो मैंने बोला था कि यहाँ से लगा के
Respected dignitaries and the Professor Sankar, Head of the Department of Mechanical Engineering, SRM University, Professor C. Jaykumar, SRM University from Chennai, and my dear colleagues and the participants from the different institutions. Actually, I am Dr. Palani Kumar, the Senior Professor and the Principal, SRM Institute of Technology, Chennai. Actually, we are having the research on mechanical engineering into diversification into material science and engineering. Actually, my achieved text is 65, and I have more than 15,000 citations, and published more than 300 papers in reputed journals, and also one of the world top 2% scientists on material science, combined by Stanford University. So nowadays we are working on application of artificial intelligence in manufacturing engineering and material science and engineering. Especially we are concentrating on heuristic algorithms. So applying the heuristic algorithms for modeling and optimization of the manufacturing processes, even materials technology. So actually, when you are going to take some simple algorithm like fuzzy logic, if you are going to see the fuzzy logic, suppose even in your home you may have washing machine. How this washing machine is going to set the water level and other thing. So this is mainly based on the fuzzy logic. What they are doing is they are following the if-then statement. If I am pouring 1 cup, then 1 liter of water is going to be filled. Suppose if I am going to put 5 cups, then 5 liters of water is required. Like that, we must have to write the program, and based on that, or even you can make use of your MATLAB. Then you are able to run the program, and we are able to model the process. So the modeling and the prediction of the manufacturing process is very, very important. So in future, prediction is very, very essential for any manufacturing process. If you are going to introduce something like machining process for a new material, how we are able to fix up the different cutting conditions like speed, field, depth of cut, etc. So these can be easily predicted by means of using the artificial intelligence based algorithms like neural network, fuzzy logic, or something else. Not only this one, we are able to optimize the results also. In which condition we are able to get the true results. So even previously, the people, we have used statistical analysis, using regression analysis and response surface methodology, and many statistical analysis are there. Using that statistical analysis, we have analyzed the process. If you are going to analyze this process by means of using this statistical analysis, we are able to get only the approximate result. But if you want to get the true result, then you can apply for a artificial intelligence based algorithm. When you are going to apply the artificial intelligence based optimization algorithm like particle swarm algorithm, even Fox algorithm, even water algorithm, it is based on the day-to-day analysis. For example, if you are going to see that water is only flow from the top to bottom level, based on that they have written some heuristic algorithm. Then this is applied to our process. When you are going to apply this process, we are able to optimize the correct result, so that even if the result is, for example, if I am going to cut the material by means of using 100 RPM, 1000 RPM, 2000 RPM or 3000 RPM. But the true optimization may rest at 2400 RPM. How am I going to say that 2400 RPM? So this may be set by conducting the number of experiments, and if we are going to give this input to the artificial intelligence based algorithm, then we are able to analyze the result, and even if you are going to get the correct, it is easily possible by means of using this algorithm, and correctly you are able to get like 2400 RPM or 2418 RPM or 2520 RPM like that. So this can be nowadays easily. Everywhere the people are talking about the AI. So nowadays the mechanical engineering is going out. So every people are going to concentrate on artificial intelligence. Everyone the people are talking about the artificial intelligence. But the manufacturing industry is growing day by day. But the students are not willing to join mechanical engineering. Why? Because so they are willing to work only in the white collar jobs, not going to work in the mechanical systems. But nowadays, every mechanical system is converted into automatic system using robotics and artificial intelligence. When we are going to use this robotics and artificial intelligence, even in Chennai, we have TIMA, Thirupati Industrial Estate Association. There, Tamil Nadu government, they have set up their own center. The manufacturing center, smart manufacturing center. So in this smart manufacturing center, everything is controlled by means of using the computer. So even we can, suppose if we are going to use a cutting tool, you may say that the cutting tool is worn out after using to 2.5 hours or 3 hours, whatever may be. How am I going to know whether this cutting tool is going to the wearable condition or not? So that can be decided and that can be predicted easily by means of using the artificial intelligence algorithm. So the people, they have used even in olden days tool condition monitoring. So when the tool is reaches to the particular state, it automatically the machine is stopped so that we have to change the tool. So like that, each and every step, everything is controlled by means of using the artificial intelligence based algorithm. So that the artificial intelligence based algorithms are very much usable in materials and manufacturing processes. Even if you are going to have the material, so Saad has presented many images using STEM and using microscope and everywhere. How we are going to analyze this? Even that image also analyzed by means of using the image processing which is connected to the artificial intelligence software. So that we are able to analyze the image very much easily. Using that image itself, we are able to obtain the optimal condition and also we are able to predict the process, whether the process is going on correctly or not. This can be easily predicted by means of using this artificial intelligence based algorithm. So that in materials and manufacturing process, we are able to use this heuristics like algorithms. So in these algorithms, so truly giving the true nature of the prediction and optimization. We have conducted experiments on drilling process, even milling process and many other processes. So for which we have implemented the artificial intelligence based algorithm. Suppose we are going to see that the National Journal of Interactive Design and Manufacturing. So in this journal purely they are publishing only the papers that are related to the modeling and optimization of process parameters. If you are going through that, you are able to see that the artificial intelligence based algorithms are very much used in the different industry and also day-to-day work we are able to apply this concept. So these concepts are going day by day and if you are able to apply that and if we are going to have the different kind of, even we have prepared an algorithm that is called as 60-40 algorithm. So in this 60-40 algorithm, we have implemented that when the process is 60% correct, 40% it is going on in the another state. How we are going to control this? For which we have written some programs using Python. Then we have applied. But as of today, we are able to get only the 70% to result. But we are trying to improve it to the 90%. So that this algorithm can be very much easily usable for manufacturing prediction and also the optimization. So that artificial intelligence based algorithms are very much interested nowadays and it can be applied for any process, even material science and for the image analysis, image prediction and image optimization. So that if we are going to, in mechanical engineering, if you are going to apply this kind of new concept, definitely the mechanical engineering will grow and definitely we will evolve in the market and more people will follow the mechanical engineering, and without the mechanical engineering, nothing is possible in the world. You may know that even if you are going to manufacture this, or if you are going to manufacture the computer, everywhere the manufacturing engineers are required. But the manufacturing engineers, they must have to stick to the new technology and the terminology. If we are using it properly, definitely we will evolve and the mechanical engineering reaches to the certain other heights. So thank you for the opportunity. Thank you. Thank you very much.
Thank you so much, sir. For any queries or questions, you can mail to us. In the session chairs, we are having with us Dr. Hazur Singh, Professor and Mohan. And in the session co-chairs, we have with us Dr. Pradeep Kumar and Professor Ajay Sharma. Next, we are having our talk with Professor Engg from SRM University, Australia. He is co-director in Space Technology and Industry Institute, STII, Director Microscopy and Advanced Analytical Facility, MEAF, and Senior Lecturer, School of Engineering. This title of the talk is Unlocking the Potential of High Entropy Alloys, Innovations in Surface Coating and Technology at Swinburne. I would like to request Professor Andrew to kindly deliver your talk, and according to the scheduled time for the presentation, so you have, sir, 20 minutes. Thank you, sir.
Okay, can everybody hear me?
Yes,
Can everybody hear me?
yes,
Yes, yes, sir.
Okay, let me just share the screen then. Screen number 2, I think, is the one. Okay. Can you see, is it okay with the screen?
Yes, sir.
Yeah, okay. Let me just move this away. All right. Today, thank you again for the invitation to participate in the AFMT MME 2005. I think the last time I spoke to you guys was probably about 4 years, 5 years ago, definitely before COVID. So very delighted to share our various innovations in surface coatings at Swinburne University. My name is Associate Professor Andrew I representing a lot of my colleagues, including, I don't know whether Amy is in the audience, but Amy's work will also be presented here. And we also have a lot of our PhD students and postdoc works being presented today. So as I mentioned, I'm Andrew, and hopefully that I will be able to keep in the 20-minute talk. So where do I come from? I come from Melbourne. We just had the Australia-India Test Series, and you'll be familiar with Melbourne, the big Boxing Day Test match. Just after Christmas, we will go into this big stadium called the MCG, and this is where we are. And in Australia, we have this culture of actually acknowledging the traditional owners of the land, and I just pay my respects to them for when most of this research has been created. So Swinburne is a technical college that was established in 1908. We gained university status in 92. We are sort of well ranked, 45 in the 50, under 50. But I guess the most proudest one that I could relate to is that we are the only cooling facility within Australia. So we offer a wide range of cooling facilities from thermal spray to laser, and we also create materials. So we also make various kinds of powder. So we're located in Melbourne, in southern, sort of the south part of Australia, if you have the map. The technical leads within our group is both Professor Chris Brown and myself. I'm also the current president of Thermal Spray Society, ASM International Thermal Spray Society, and I know next week is actually the Indian National Thermal Spray conference. So Chris will be there, my Vice President Kamal Long from Delta will be there, and we hope that in the near future, ASM will be able to bring an international sort of symposium into India. I've been to India many times. The last time when I spoke, as I mentioned, at IT, I think the conference was IT Ropa, and I was there in person. Unfortunately, this time the notice was, and then also because of schedule, unable to come. But I've been in thermal spray in the facility at Swindon for the last close to 15 years now. I've been working a lot with various job shops to big clients like Boeing on various technical challenges that they have to functionalize their surface, to repair and do overhaul. And today what I'm talking about is high entropy alloys. I think a lot of you here in our audience would know what high entropy alloys are. I won't go into too much details, but basically in about the early 2000s, about 1992, 95, around that period, there was an article written by Professor Rajaratnam from ITS about cocktails, wonderful magical cocktails, metallic cocktails, and that was sort of the highlight of how one of the magical cocktails was actually high entropy alloys. So high entropy alloys get their sort of their name from the word entropy, the entropy configuration. When you start to mix many different elements together, has an effect of raising the entropy. So once it's above a certain configuration, 1.5 R, you get sort of the high entropy effect. What does it mean? You actually get simple solid solution form, you get sometimes multiple solid solution form, you get less intermetallics, and so on and so forth. So people believe that this is another way of actually alloying. So instead of what we do traditionally, like stainless steel, we take iron and we start to alloy it with finer elements. In high entropy alloys, the concept is you are alloying the atoms, and you want to place the atoms in certain positions so they form the solid solution BCC FCC phase. Many literature and sort of papers have been published over the last 2 decades on how to create them, and then our group, what we do is we use them as functional coatings using thermal spray, laser, sometimes the PVD-CVD way. I teach undergrads, and whenever I try to explain to them what's high entropy alloy, they look at me in stunned fashion. So how I actually explain high entropy alloys to them is a bit different. Is this slide whereby you watch the basketball game, high entropy alloy. It's like I was born in the Chicago Bulls era. So Chicago Bulls had Michael Jordan, and Michael Jordan is the steel. And then you've got all these supporting cars. You add a bit of chromium, you get the nickel, so you get pre properties, you get anti corrosion properties, and then you want to add a bit of manganese and moly for machining and heat treatability and all that. So you get stainless steel, 3R6L. Whereas for the high entropy alloys, what you're trying to do, they can call also multi-principal alloys, and we call complex concentrated alloys. Yeah, all the same terms. It's an all-star game. You actually put everything in there, and as what Professor Rajan said, you get the cocktail effect. You get the sum of all parts, and it becomes a designable alloy. Say you want it to have corrosion resistant, wear resistant, you can actually tune it. So yeah, the atoms are being alloyed equally, and sometimes equally, sometimes non-equally also. So if we have the sort of the non-equal atomic entropy alloy. And they have wonderful properties. Like from the previous example, you will know that if you have all-star versus normal team, the all-star team usually wins, right? I should actually change it to a cricketing example next time. Anyway, in our group, what we do a lot is we actually use this as coating. So we create the powder or create the wire, and we actually then spray them. So we have both the equiatomic, meaning same number of atoms. We also have the non-equiatomic sort of alloys that we work with. And as you can see here from the graph on the right, you can see there's an explosion of people actually coding various kinds of HEAs, and over the last 10 years or so, or 15 years when we captured this graph, over 1,000 papers. Probably in 2025 that we will break the 2,000 publications for the year. And we certainly have done like special issues and all that on thermal spray. Ashok has published a review paper that has about 45,000 views, and I think Amy is also one of the primary co-authors in that paper. The direction that our group do is we don't only just work on the coding, but we also work on both designing and also matching the properties. So we often have an iterative design whereby we go look at, okay, how do we want to design this? What are the phases that we want? We use thermal software, we use computational means, and we actually then do the creation of the material and processing it, and then matching the properties, and sometimes going through the start. So we sort of do this sort of iterative work, and so far it has been quite successful, and here today we'll share some of the various results. We have a number of production capability. We can ball mill it, we can also add the cuts and atomize it, and so on and so forth. So the previous speaker talked about using AI and all that. That's certainly a very hot topic of how to use AI to actually design your alloys a bit smarter. When we first got into this and understand this, there wasn't that wide use of AI. There was definitely a lot of empirical methods, meaning using your first year undergraduate material science course, Hume pottery rules, making sure that the radius are about the same, the chemical charge is about the same, and so on and so forth. So a lot of empirical calculation, that's one way to do it. Second is to actually use calculator. And certainly we learned a lot from Professor Murthy, who is very instrumental to some of our initial work and continues to be so. I'll share some of the results in a while. And then even now what we try to do is to incorporate machine learning with all these different methods to try to get to the right kind of alloy that we want to design much faster. So our first journey to HEA was through Professor Murthy, as I mentioned. He and another colleague of his, Professor Ravi, came down with powder that we then be able to create a coating with. So here we present to you the actual one of the very first HEA, thermal spray HEA coatings that was created. Definitely first in Australia, I'm not sure in India, but what we are able to do is to prove that hey, you can actually take HEA and create it as the coating and functionalize it as coating. So you can use it for wear resistant, corrosion resistant. You can use it for various functional applications. And we found that hey, the coatings produced does retain also elements of retain the HEA properties. And we can then also start to control the amount of porosity or the amount of oxides and all that, because if you are looking at the thermal barrier sort of coating, you might want porosity, but or biomedical, you might want porosity. But then if you are trying to look for wear or something that is corrosion resistant, you do not want that much porosity. So we started our journey to look at how we actually control some of these processing, and you will see that we are able to get very dense coatings, but also very porous coatings, and various composite coatings too. So this is a plasma spray hydrogen alloy coating, ALCOCR, FENI. But that coating got us thinking, right? We've got a BCC powder, majority BCC and FCC, and then when we start doing that thermal spray, which is, if you think about it, is actually a rapid heating, meaning you heat up the material, you melt it, and then you quench it. You got the rapid heating and quenching process. It turned from major BCC to major FCC. And then by looking at some of the TM results that Amy did, we are able to see, okay, what actually happened. Some of the aluminum diffused out, which form aluminium oxide whites remain, and we have our BCC and FCC phases. Some of them were not fully melted, that's why they retained some of these phases. So we can actually now explain, right? And it was in the GEOCOM paper that we explained what actually happened, and that was very good, because we are now able to if I can, so the next slide, we are able to then look at how the elements flow within, in the metallurgical sense, how the element flows within the melt pool, or when as it quenches, and then explain the phenomena of how the coating is involved. Very good. But then we started to ask the question, can we actually control the amount of phases in there? Can we actually know if we want to retain more BCC, how do we actually do it? So that was sort of a journey that we started, about 10 years ago. We then went back to say, okay, how do we actually design these alloys first? So we went back to the drawing board, started to, okay, we start to look at, can we actually find something very stable that doesn't have that kind of, transformation? So we went with that, and then quickly we'll find out that, you have a sort of computational problem, right? If you want to have like 5 elements with a 30 million combination, if you start looking at not only equiatomic, many, or if you even look at, just equiatomic, you have 30 million possible combinations. If you look at 10 element equiatomic, you have about 1 trillion composition. Then you start looking at non-equiatomic, which is where I believe has a lot of potential. Right? I remember attending one of Cantor's talk. He was talking about Brian Cantor, who is one of the co-founders of DAY-2. He was talking about, they chose that because it was convenient, right? But then he believed, and he wrote it in one of his papers, that you can actually alloy with various atomic ratio. And I believe that is one of the biggest potential that people can start looking at various compositions or various atomic ratio. And you can see that now we have 1 trillion combination. To make that happen, it is actually very complicated, right? So here, Mr. Bart Simpson's, and one of the famous model paintings, right? That it can be a headache. So what we started to do is we started into the CalFab simulation through also talking to people, the global experts like Professor Murphy, and we started looking at CalFab, but we also quickly found out in terms of CalFab is it only allows us to do when you start plotting the diagram, it only tells you equilibrium phase diagram. So people here that I believe here most of you have a metallurgy background. If you have only the sort of equilibrium diagram, that is somewhat limited, because if you start looking at the process that I described, thermal spray or even laser cladding, you have a rapid melting and rapid cooling. So how do we actually capture that? So that led us into something called the shark simulation. And what happens is shark simulation is basically like a pouring effect. If you look at some of the textbooks, they start talking about non-equilibrium cooling, and that's you can actually simulate those non-equilibrium cooling by triggering the shark simulation effect. So we started to do that, and this is the study that I'm presenting, that we actually started to investigate whether we can actually use shark simulation in our study for thermal spray deposits. So how well shark simulation can be used to predict our our building final composition. So what we did was we took one, two, three different compositions of coatings or HEA, and we deposit them as coatings. So H-fuel1, high velocity oxy-fuel, is actually a like combustion process. And again, it is a rapid heating and cooling. HELA, which is a high-speed laser. So it's again, using a laser. They have very sort of particle speed. They have the same concept of heating up the HEA to melting point, and you're quenching it. And we want to see how well we can actually trigger that and take some predictions. So what we did was we asked one of our PhD students to make all the empirical calculations, and you can see that from the empirical calculations, he's able to sort of, whether it is intermetallic formation, solid solution. So from various models that he chooses, he can actually make some of these predictions. But then that seems to be not enough. So what we did with is in Calfat, we started to simulate the equilibrium, and then in this alloy, the CALCOCRFE-NI alloy, we predicted that in equilibrium you will have, or it predicts that in equilibrium the B2 phase is the primary phase. Then after that we've got the BCC phase right after the B2, and so forth. In shark simulation, it's a bit different. Shark simulation, you still form all the different phases, and what happens is you can see that there's also FCC being formed as you create the alloy tools. So we did that, and what we did is when we got the powder, we also created so we did the powder, we did XRD, we also created coating, and then we started to measure the various amounts of the FCC, the BCC, and so on and so forth. And then to verify that with the Calfat curve that we can create. Without going into much details, the paper is published here. We have found that the shark simulation is able to predict very good agreement with what happens in the thermal spray process, and also in certain laser process like those that are very rapid cooling and quenching. So that forms sort of our basis of what we believe can allow us to control the amount of lasers in a coating. So if you want to control the amount of BCC and FCC, you can then do that by designing the alloy, but also designing your cooling rates. Along the way, what we also did was we looked at, are we able to deliberately, not just from a single powder, but are we able to actually deliberately create dual phase HEAs? And I showed that this work. And what happens is we took two different HEAs, one BCC, one FCC, and we mix them together and see whether we can retain them, and what kind of properties can we get from them. And here you can see that we have a FCC powder and a BCC powder, and we mix them in different ratios. I think it's A12, yeah, A12, correct. And then what happened is we then spray them through, in this case we used, I believe, HEA1. And you can see now, from the first coating that you saw to now, we can actually control porosity. This is much lower porosity. This porosity probably is like 4% or less, because we use a HEA process, and we are now able to get a very dense coating. But this coating has both hard and soft phases. So your BCC is usually your hard brittle phases, and your FCC is usually your soft ductile phases. And you can actually probe that using nano indentation and all that, which we did. I think subsequent slides have other examples of that. And we are able to then get these different kind of wonderful properties. I think the driving home point for those that are still studying material science, listen to your year one lecture, because we did the rule of mixture, and then we started to calculate the rule of mixture, the phases, amount left over, and the properties of it, and it does correspond quite well. So, and here is the nano indentation results, and you can see that we got a hard soft effect because you've got a bimodal distribution in your not only indentation, and also we can actually track which is the hard and soft from the contrast map, also from the hardness map, and we can then sort of design this kind of full phase HEA. But it sort of led me to sort of also think about, can we actually have a powder that have actually DCC and FCC in it at the same time, right? So one single powder, instead of having the mix, can we actually have one powder that have DCC and FCC in it, right? So it's actually published already when we started looking into it, because in 2013, Shen Guo from Chalmers University, which is also another quite early adopter of HEA, published a paper that calls it sunflower-like solidification. So you have, your DCC and FCC in here, and sort of solidifies like looks like a sunflower. Very pretty. I love to look for nature in some of these micrographs. So what we did was we take. Can we actually get some of these eutectic hydrogen alloys, and can we actually deposit them as coatings? And can we actually control through the heating and cooling, through the processing, the various layers of FCC, DCC, and how the distribution looks like? So what we did was we chose the alloy, which is quite a famous alloy now, a lot of people using it, AlCO-FeNI 2.1. So you need to have more nickel in this case. And what happens is we use the ELA process, which is a rapid solidification process, to reduce dilution. We're also looking at this as an alternative to ink canal. So instead of using ink canal, can we actually use this as a ink canal replacement? So when you look at the powder does looks like does have the FCC and VCC in there. You can see beautiful FCC VCC patterns. The pink color one is the FCC, the VCC and V2 is the blue color. So we can get those powders, the atomizer, they are really, really nice to look at. And then after that, we create the coating. Again, we employ the shock simulation that we spoke about just now, and we can see that with controlling, the shock simulation and all that, we can actually predict wind field. And this is shock simulation. Shock simulation says that we should get about 70% FCC and 30% V2 or VCC. And you can see here when we did the review, after we get the coating, we do XRD, we can get 70-30. Not perfect agreement, but it shows that shock simulation is able to predict. Then we start looking at the alloy. This is from literature. We also talk about this is we did HF and laser clad also, but we can see what is the DCC reaches when the FCC is reaching, and we can then calculate this, and we actually can control this because in the HF and laser clad we can control the amount of DCC and FCC actually. And that was one of the reasons why we wanted to use shock simulation, because we can then do different kinds of simulation. We start looking at the grains and how to orientate the grains, and we can actually orientate the grains by controlling the cooling rate, how the laser moves, how the processing parameters that you can see here. We can actually get various kinds of laminar forms, dendritic structures, and all that. When you start studying them in nano properties, you can actually have a very hard layer, same partner, but very hard layer on top, very soft in the middle, and that's something that you can then design your HEA with for various kinds of functional applications. We also need cold spray we also do cold spray here at uni, and cold spray is sort of it's not a long phase change, but this I slot in this slide to say that if you cold spray, what you get is plastic deformation. You can talk about DRM, direct getting rid to crystallization and all that. We are still studying it, but cold spray is another area that we look at. we don't need to do struct simulation. In this case, whatever powder they get is whatever mostly what things they get. Mainly at the grain boundaries whereby there's some recrystallization, maybe you'll get some different properties. So you can see some of these. I'll wrap up very soon. I know I'm going over time. I will really focus on quite thick coatings. And here we have also worked with Dr. Joshi from University West, which some of you might be familiar with, to create the first suspension HEA coating. So the coating is made from suspension. So we make powder, we mix it in the liquid, we deliver it in the plane, and we created that coating with Dr. Joshi's help, or Professor Joshi's help. Published that in Intermetallics last year, I believe. We also have been, this one was accepted last week already. So this we have created also the world's first carbide-based HEA. So a lot of people have been mixing carbide, but what we have done is we have agglomerated and sintered powder of HEA nature. And we have sprayed them, so you can see the white color of the drains are actually carbide, and then the binder is actually a HEA. So we've created that powder, we've sprayed them, and we believe that would be another way of you getting wear resistant, corrosion resistant coating at high temperatures also. So here are some of the properties. I think I'll close this and then after that allow some questions. I hope that, through this 20-25 minute talk, I've shown you that HEA is actually very interesting to study, very sort of unique properties that we have come a long way through empirical studies all the way to now using ICNE approaches, through using AI approaches. As I mentioned, the driverless atomic HEA is something that I think will unleash a lot of various structural property combinations. Our group has been looking at both cost-effective and lightweight HEAs for various types of applications. The world's running out of cobalt, running out of nickel. We use that in our batteries. So we're also looking for those that are cobalt-free and nickel-free, or ways of recycling or using some of these. So we believe that we can't do this alone. As you can see that we collaborate with a variety of partners, including the IT Mobile and also IT Madras and IIT Hyderabad. We collaborate a lot with them. We also love to collaborate with others in India. We believe that there are many ways of creating HEA. We have a few ways to create. I believe there's many ways that we can work together. This is sort of the dawn of a new way of alloying. Collaborative research is needed. Certainly across material creating to resurfacing. So that we don't believe that we can do everything alone. So collaboration is very, very important. So with that, I acknowledge my funding agencies, the Australian Research Council, and also the various collaborators and so on and so forth.
Thank you.
And then these are some of the papers. I'm open for some questions if there's any. Please.
Thank you so much, sir, for your very insightful session.
I'm sorry for going over time.
If anyone is having any questions, they can ask. Or if we are having any questions or queries, you can send through the mail, as we are falling short of time, so you can share your queries and questions through the email. Thank you so much, sir, for your very insightful session. Thank you, sir.
Yeah, so last point, if there's no questions, save the date, end of the year, 1st to 3rd December, ASM TSS is organizing a conference in Melbourne. So if you are interested to visit Australia, see some kangaroos, see some wombats, have some good food, please save the date. A poll will be going out very soon. And as I mentioned, TSS will be looking at hosting or also doing a local event in India, most likely in 26 or 27. We are planning, and we would love to bring a Campus Space Society event to India. With that, I shall say goodbye. the chairs allow me to do that.
Thank you.
Thank you, Dr. Andrew, and we would be very happy to connect with you again. Thank you so much. Thank you for that invitation also. Thank you, sir.
Sorry? Was there a question for me?
No, sir, no, sir. Thank you so much.
Okay, thank you so much. See ya. Bye. See you, Professor Apri.
I see you. Okay, see. Nice see you. Thank you very much.
No worries, my pleasure always. I'll see
Thank
you.
you. Bye-bye.
And now is the time for hiking, and it is there in this block here. Right? So I request the students, please wait, let the kids go there, and then I will join with you. Okay? So please stay for a bit. Thank you.